Thank you, Alessandro. Thank you, everyone, for being with us today. So my name is Claes Hjort. I'm a professor in material science at Uppsala University and coordinating this European project, SINTEC. And in SINTEC, one of the major objectives is to create a new industrial technology for smart and stretchable patches. And I will talk a little about the SINTEC module and the smart patch printed circuit board technology. So the principle is to go away from the rigid and flexible printed circuit board technologies to stretchable and comfortable systems for the human body. The project as a whole is to provide sensor patches that can be used at multiple times for longer periods for anyone, anywhere, anytime. And by that, not only providing use when you are still at the hospital at home, but permits an active life, vigorous action, sweating, water activities. In addition, we want to show the advantages when having stretchable sensor patches and not just flexible systems that are compliant by using a groundbreaking sensor node technology and applications within medicine and sports performance. So, smart patches, where are they today? For those of you that are not following the market, it is booming. So within 2 years, it just doubled till 2021. It's going fast still, and many of us believe that the market prediction 2 years ago of $30 billion by 2030 will be surpassed. The main market is for patient monitoring, or what we call continuous remote patient monitoring. Not just having it at doctor's office, in the clinics or at the home, but all the time, continuously. And the focus is on diabetes and heart conditions, but it's spreading to more and more applications as we see the advantage both for society, those that have chronic problems, and the comfort for both patients and their family. These are made by combining multi-use modules with disposal patches. You're using flexible wire boards, rigid modules, and compliant patches typically. Here are examples, if we look to that. Yes, there exist in very rare cases electronic tattoos, but because you cannot use any battery, you need near field communication, so you need an advanced infrastructure, or you can just download information now and then using your mobile phone. Rather, it is the systems with rigid flex printed circuit boards, packet-in elastomers, or batch-produced printed wire board technologies, most commonly using screen printing. This is from Benelli AB in Helsingborg in Sweden. That's the largest producer in Europe. This is the SINTEC hardware offering. Soft and stretchable sensor patches, thin and soft multi-use modules, and the module is set under the patch for comfort and protection. Typically, if you're a sports performer, that you can put on your racing suit without disturbing the multimode structure that usually is on top. The SINTEC technology is building on one of our partners, Mycronic AB's solid mount technology for manufacturing of putting assembly of rigid components on printed circuit boards. We learned that the low temperature processing of these manufacturing line is very well suited for additive manufacturing of stretchable printed wire boards for smart patches. And with that, we can also provide individually tailored smart patches if needed. So the manufacturing, we are at the final spout of this project. We have established a semi-automated production for large area rigid stretch printed wire boards. We have introduced flexible interfaces between the rigid and the stretch, and we have precise patterning of liquid metal alloys for stretchable interconnects with line width below 100 micrometers or 1/10 of a millimeter. We can also increase the throughput and by that reduce the lower cost, but then we have to do it at lower resolution. The most recent improvements for allowing vigorous movements and heavy sweating, which has been sweating, we have start using sports tape. So we laminate a thin printed wire board onto commercial sports tapes. We are using molded protective encapsulation of the multi-use module, a new flex contact to connect to electrophysiological patches, and we have been changing from coin batteries format to lipo batteries, just like in smartwatches. Here is examples of bioimpedance measurements. So you can just see the breath rates monitoring going up and down. And here is an example of ECG electrode where we have one long stretchable flat cable going up. And finally, we can also do multi-layer digital printing. Once again, line widths below 0.1 millimeter, pitches below 0.5 millimeter, and vias a little bit more than 0.2 millimeter in size. So my take-home message for you is we use multi-use modules for disposable patches. We have ST microelectronic sensor board for motion, so pulse, ECG, bioimpedance, and temperature. We can provide rigid stretch printed wire boards based sensor patches with wireless electrophysiological readouts, for example, ECG monitoring. We can apply these printed wire boards to sports tape, so providing a skin adhesive smart patch well suited for the active motion. And we can do large area manufacturing of printed wire boards using Micronic's solid surface mount technology machines. With that, I thank you for the attention and leave for the next speaker. Thank you.
Thank you, Claes. Thank you very much. I don't know, Sarah, if we have some time for a question, or we would like to leave the question at the end of the different speech. I don't know, remember. So
I think you can go with your presentation.
Okay.
And if someone has any question, please, you only have to raise your hands up and we give you the floor. Okay?
Okay.
Perfect.
So thank you again, Claes. Just a question maybe useful for everybody, just to put on the floor now. After the speech, after the workshop, we will have also other questions. But in general, just maybe is useful for everybody. The electrical characteristic of what you are developing with stretchable electronics is comparable with what is existing now for the, let me say, classic rigid one as a number, for example, or layer you theoretically you can address, or the dimension of the traces, or this kind of stuff?
I would say that we are still not mature enough to make multi-layer stretchable systems. So 2 layers we do, but not with high maturity. The ordinary printed wire board technology, I would say, is mature and provide as good as flexible printed wire board technologies, but no multiple layer printed circuit board technology needs further development before industrialization.
Yeah. Thank you, Kras. I go with my presentation. I try to share the screen. Let me know if you see my presentation or not.
Yes.
Yeah, my PC is very slow. I don't know if you see my presentation or the comments.
No, we can see the presentation correctly.
Okay, thank you. So, as I said before, I don't know if I said before this, but I'm Alessandro Gumiero. I work in ST, in a remote monitoring group, and I will go to present something related to what Klas already said about the SINTEC project, the aim of the SINTEC project, let me say, what we try to develop under a hardware and mechanical point of view to guarantee the things already introduced by Klas. Let me say, or better, let me start from the aim of the project. And as Klas already introduced, the aim of the project is just to, in general, simplify and enable the usage of these of some complex exam, a medical exam, especially at home by normal users. So just to give you an example and to start from something that probably in the next presentation by Fernanda probably will be more explored, but just to give to you an idea, for example, in this case, when you are in a normal condition, for example, with tiredness, lack of attention, headache, normal condition for everybody, or maybe also now because it's the morning, we are in the morning or something like this, is a normal situation, but it could be correlated with something, with some bad disease. So if you want to understand this, obviously you have to go now to an hospital to do a very complex exam, complex and very invasive. You have to try to sleep as in the picture in the slide. So this is a very good picture. Let me say the situation is worse than this. And try to sleep, I repeat, for 1 night, 2 nights, if you cannot sleep for 1 night, and you can discover if your headache or your continuous tiredness is related to some disease. Or you can keep your headache and go ahead as we do usually. But for example, and this is the aim of the project, what if we would be able to reduce or to simplify this kind of exam to something more simple that can be used by a normal user, not an operator, and in a very common and comfortable way. And you can imagine that if you can pass from having a lot of cables, wires on yourself, to something very smaller. This is on the picture you can see a real board developer for SINTEC attached to your body in a stretchable manner. You can imagine easily that is more easy, sorry for the repetition, to sleep, obviously. And also on another other end, you can also imagine to have other kind of exam, not related to the sleep, maybe related to the cardiology, to the heart. And usually in normal situation, you have to go to the hospital again, connect your body to the machine and have a day's monitoring. Or you can imagine to have something more simple. Obviously, just the premises is that we don't want to substitute the physician or do the job of the physician, never. We would like just to simplify the life of the physicians, have a more robust or more extended screening to enable more reliable diagnostic and done by the physician at the end of the story, always. So in this context, there is what we call the remote monitoring thing, and what we applied in SINTEC. What we call the remote monitoring thing is just this: develop application to enable complex exam at home for the final for a normal user and not a user, not an operator or operators. In this way, without substituting ourselves to the physician, as I said before. So try to do this being very simple, very small, very low power, very comfortable. Because I repeat, we are not talking about operator, expert operator, but normal user as we are. So the first thing is try to put all kind of reading, a different kind of reading, medical reading in a unique device, reducing the dimension of the device and allowing the data fusion of different parameters at the same time. So this is very important to enable different extraction of parameter and study of different diseases related to not only one parameter or one signal, but to the combination of different signals. On the other end, we have the necessity to reduce the dimension, as I said before, but also to reduce the power consumption and also the complexity of the reading. So we are not talking about a complex medical machine, but we are talking about, in many cases, or in all cases, it's something simpler. And to guarantee the simplicity of the solution, the final solution, maybe it's better to start from what ST, in this case, is able and is strong to do. So integrated circuits. And in many cases, the integrated circuits where we started are not developed or designed at the beginning to be medical, but in many cases, quite all the cases are designed to be very low power, very low with low complexity, and to be mounted and embedded on consumer devices as a mobile phone and something like this. In this example, and this I reported two examples of what we actually used in the SINTEC project. We have a spectrometer originally designed to correct the white on normal imager on your mobile phone, for example. On the other picture, we have a MEMS accelerometer plus gyroscope plus a peripheric able to detect potential, not originally designed to detect the biopotential, but we try to use to detect, for example, ECG or EEG. In this context, we have also the necessity to work to simplify the hardware and the impact on the mechanical part and the user, on the final user. We have the necessity to work a lot on the algorithm and to guarantee to be able to extract the same parameter with the same quality, starting from signal, but maybe starting from less signal in respect of the normal practices. So here I reported two examples where we extracted the SpO2, for example, and the blood pressure starting from just one photoplethysmography signal. So instead of usually in the medical practice is done so starting from two optical signal for the SpO2 or other signal for blood pressure. But these are just only two examples to explain how we try to simplify the starting point of our reading and trying to keep and maintain the medical grade performances. So here just a picture to show to you what we done, but class already showed this point. We did, I have to say, a lot of different trials to correct and to reach and to fix the issue, and we are continuous to do obviously this kind of job, and we arrived to a final, let me say, structure of a SINTEC project. The SINTEC architecture, what we do, start from a multimodular concept, so a system where we are able to connect different devices put in a different places of your body. So depending on the case, to monitor the ECG, to monitor the photoplethysmography signal, optical one, motion, and these kind of things, and the possibility to relate, to correlate, to connect all these devices through a gateway capable to collect all different signal and enable, as I said before, a mixed computation of this signal, or also a single one, or using a single one, or this kind of things. So to enable to be very flexible also under point of view of architecture. We developed a structure to be always flexible. I'm repeating a lot the word flexible because all the things, all the stuff related to SINTEC project will be as have been designed from the beginning to be flexible, so to enable to change a module without changing the final architecture, to be able to connect a different module to the existing module and so on. So we developed a structure to develop the module, a rigid module with the electronic part, and to connect with and through the stretchable patches developed by Uppsala to the other modules, so to the battery or to the other things. We have the possibility to have modules, electronic modules without battery or with battery already connected, and the possibility to work on the module and realize the module in a flexible manner or in a stretchable manner. The things, and one of the major issues we had from the beginning was to connect the rigid part to stretchable part and guarantee a reliable contact, because it's very easy to break. You can imagine the contact in between these two things. We elaborated, we designed a intermediate, flexible intermediate to avoid to have this direct passage from stretchable and rigid part. You have to consider that it's not possible to put direct the chip on the stretchable part. It's possible to do, obviously, but if you want to guarantee something reliable, something real usable, you have to study a methodology, and we did with this models approach. The more general architecture, you have the module, you have the stretchable patches that connect the different modules, can connect them battery, different modules, depending on the use case and on the designing. We can, in the stretchable part, can connect electrodes very far, as class already show in the previous presentation. We are able to, you have to imagine the stretchable things as a second skin, and with enhanced elasticity, stretchability. At the end, but not the end of the architecture, one of the most important points is that also we have a stretchable patch, which are able also to protect the entire solution and the device, the electronic device, because you see only the stretchable patch, and the only thing that connected the device with your skin, so the dock the device to your skin, is stretchable, so you do not feel nothing rigid on your body. Yeah, you feel something, but you cannot understand or perceive something very uncomfortable. So eventually we have the hardware developed, and the hardware developed for this, as all the things we did, we said before, we introduced it before. So all the characteristics to the possibility to embed on the same hardware a lot of different things, a lot of different reading, have the possibility to enable the data fusion and mixed computation of these different things, and keeping the dimension very low, and keeping also the power consumption very low. So we keep, let me say, a standard architecture inside our devices, but keeping the dimension very reduced. In 12 per 12, we have a lot of different possibility of reading, ECG, PPG, motion. We use to double this dimension just to add the debug interface, but it's not useful at the end of the story, at the end of in a hypothetical final product. So we were able to reduce the dimension, keep the dimension very low, keep the power consumption very low, to be able to be embedded in the SINTEC architecture system. So, and with this we are able, and we tried to detect, and we are detecting all these parameters, ECG, for example, bioimpedance, impedance of the stretchable part for the respiration, and also bioimpedance, again, for the respiration or body composition. But just to give you an example, of practical example of what we are able to do or what we are trying to address. And thank you. That's it. So, Sarah, I can stop my presentation.
Yes, perfect. If anyone has any question, please put your hands up and we will give you the floor. Okay, I see one hand up from Professor Herrera.
Yes, thank you, Alessandro, for your speech. And of course, I am interested in this question. So I ask you, what about the using QR in these types of application? Thank you.
Yeah, the QR gives us the possibility first to use general answer is to use ST components in this solution. But above of this, more important is that the QR is not, as I said, originally designed for to be a biopotential reading, but has been originally designed to be very low power, low complex, and these characteristics are very important to reach what I tried to explain before. So starting from this, we just wanted to demonstrate that it's possible to have a medical grade reading from this. But as I said before, QR as other things are not originally designed for this, but enable this kind of reading. It's very simple, let me say, and already embedded with, in that case, MEMS reading. So gyroscope and accelerometer is very common situation to have the necessity to read the ECG, for example, coupled with accelerometer. So if we are able to demonstrate that it's possible to detect a medical signal coming from the QR, obviously the job is quite done to have a very competitive medical application.
Thank you.
Thank you for your question, Fernando. So I think that Sarah, we can continue with the presentation of Luigi that will introduce more generic, quite generic introduction of wearable application related to the job they are following in Polito and also with us. So please, Luigi.
Thank you, Alessandro. I would like to ask you if you can see my presentation and you can hear my voice.
Yes, we can see the presentation and we can hear you.
Yeah,
okay,
yeah.
Thank you very much. So, good morning, everyone, and thank you for being here. First of all, I would like to thank the organizer for having me today here. I am Luigi Borzi, and I'm an assistant professor at the Department of Control and Computer Engineering at the Polytechnic University of Turin. Now, with this presentation, I would like to provide you with a very gentle overview of the wearable technologies and their application in healthcare. And in addition, I will give you an overview of the main activities carried out by my research group. So, the human body is a very complex machine that works thanks to the synergic interplay of different organs, systems, and apparatuses. However, humans are not perfect, and several momentary or chronic disorders can affect one or different parts of the body. Fortunately, our body communicates. It uses a series of chemical, electrical, and physical signals that, if analyzed, give us precious information about the state of health and possible alterations and pathologies. So, in this slide, I reported a non-exhaustive list of physical and physiological variables that can be estimated with today's technology. For example, the electroencephalogram measures the electrical activity of the brain using electrodes placed on the scalp. It is indeed very useful for assessing and help diagnosing different neurological conditions. It typically consists of 20 to 30 electrodes that are used and attached to the scalp, and a gel is interposed between the electrodes and the scalp to increase electrical conductivity. This is why you can see so many wires in the picture on the top. On the other end, electrocardiography measures the electrical activity of the heart. It is very useful for assessing cardiac disorders. And typically, in this case, it consists of 10 to 20 electrodes placed near to the chest. And finally, movement can be accurately assessed with optoelectronic systems. Now, these systems requires the mounting of many reflective markers on the body, on the human limbs and joints, and then a series of cameras record the position of each marker in the space and over time. Now, most of these technologies share a long setup time and they require cumbersome equipment. Indeed, they are very costly and somehow invasive, and thus they increase discomfort for patients. And finally, the presence of many wires increase the risk of noise and artifacts. The situation is even more complicated when dealing with multimodal data acquisition. For example, human kinetics or kinematics can be assessed using a variety of pressure sensors, electrogoniometers, inertial sensors, and EMG sensors. On the other hand, as also Alessandro showed to you, polysonography consists of recording EEG, EMG, and ECG, as well as oxygen saturation and respiration. Hence, the need for less invasive devices that can allow for long-term, remote, and continuous health monitoring in real-life settings. Now, wearable devices aim to overcome these limitations, providing small, light, and cheap sensors that can be worn on the body for hours, days, and even weeks. Now, I would like to provide you with a practical example, which is also from my personal experience with my dad. So, until more or less 5 years ago, my dad, who suffered from diabetes, used to measure the glucose level in the blood by means of a glucometer. So basically, it works by analyzing a small blood sample, which is typically obtained by pricking the skin with a lancet and placing the drop of blood on a test strip. Now, this test strip contains chemicals that reacts with the sugar in the blood, and these produce a small electrical current. Now, the glucometer then measures this current and calculates the blood sugar level. Now, the problem is that he had to prick the finger skin, which is not so painful if done once or twice. However, it can become very hard when doing it like 3 times a day, every day for weeks and months. Moreover, he had to manually annotate the measurement. And finally, only point measures can be possible, losing all the other information from the real trend during the day. Then, a couple of years ago, he took the smartphone in his hands, which actually is not so common, and he put it close to the shoulder. And only after a while, I understand what's going on. He had a smart glucometer, which I didn't know the existence on the market. Basically, it consists of a tiny electronic device that you can see in this picture that can be attached to the skin, typically on the shoulder or in the arm in general. Now, this allows for real-time recordings of sugar level and allow individuals with diabetes to monitor their glucose level continuously and make adjustment to the insulin or whatever other medication dosage, and also to change the food intake as needed. Now, this device wirelessly sends the readings to the smartphone application. And this solves a lot of problems, from pain to the automatic annotation and the possibility to provide alarms in real time. Moreover, it allows for continuously monitor the glucose level. Let's say typically measures are taken 1 to 5 minutes apart. And this solves also the issue of patient compliance. Now, this was just one example of the potential of wearable technology for healthcare. But in reality, there is a wide variety of sensors and devices, and several are already on the market. They have the advantage of being, very small and light, and they can be worn on the body for a long time. They are able to collect and process data in a non-invasive and, let's say, ecological manner. And in addition, they promote subject comfort and represent a local solution for long-term remote health monitoring. And finally, they allow the recording of multimodal data, including different sources, such as heart rate, respiratory rate, movement, and so on. Thus, they represent, the ideal solution for collecting large amounts of data in free living settings. And there is much more. The interesting wearable technology has led to the continuous reduction of the weight, size, and cost of devices without sacrificing measurement accuracy and processing capacity. And this has led to the development from research to the final market of tiny standalone devices that can be attached to the body in the form of smart patches, as you saw before. They have actually certain advantage over the standard wearable devices, such as the suppression of the relative movement between the sensors and the skin, and this allows also to avoid noise and artifacts. Moreover, being attached to the skin, they can precisely detect chemical and electrical signals, which can be useful in a great variety of health applications. And finally, one of the latest trends concerns smart e-textiles, or even called smart clothes, such as t-shirts, trousers, or even shoes that you can see here, that incorporate sensing, processing, and communication capabilities. Now, the latter technology can maximize comfort by being invisible to the human eye. Having said that, today we have widespread commercial technology that we use on a daily basis. The most common are represented by smartphones, smartwatches, and more recently, smart rings, which incorporate a wide variety of sensors. These record and process position, motion, pressure, sound, light, and many other physiological variables, such as heart rate, temperature, and even the conductance on the skin. The advantage is, of course, that we don't need to buy additional hardware if we own one or more of these devices. Instead, we can exploit their potential and the fact that we already wear these devices for several hours a day. Thus, this can be a minimally invasive way of recording health data continuously and process them. Now it's time for my research group, which is led by Professor Gabriella Olmo. She's both a doctor and an engineer, so she perfectly embodies the idea of using technologies for health. The group merges different disciplines, let's say, including biomedical, electronic, and computer engineering, as well as medicine and neuroscience. The objective is to provide telemonitoring solutions based on minimally invasive, low-cost and lightweight technologies. And the mission is to kind of augment health by using artificial intelligence and signal processing for personalized care, continuous monitoring, at-home rehabilitation, and support for early diagnosis of diseases. Now, the work involves the study of mostly neurodegenerative disorders like Parkinson's disease or Alzheimer's dementia in close cooperation with patients' associations, but also with several hospitals. And here I will be very brief. I would like just to give you an overview of some of the activities we do in collaboration with doctors and neurologists. Firstly, sleep disorders, because actually they can manifest up to 20 years before the clinical diagnosis of Parkinson's disease. In addition, we know very well that sleep affects physical and mental health. So there is a need for minimally invasive technology that can be exploited to provide a comprehensive sleep analysis without altering sleep itself. And in this context, we use wearable devices to record brain and cardiac activity, as well as movement. On the other hand, analysis of the human voice can bring very powerful information on the health status, disease progression, and the effect of medications. And in addition, speech disorders can also occur more than 10 years before the clinical diagnosis of Parkinson's disease. So analysis can be a tool to aid the diagnosis of diseases. And in this context, we use commercial devices such as smartphones, which are, of course, validated with professional equipment, and with the aim to perform non-invasive analysis. And finally, we analyze human movement, let's say in two different and complementary ways. First, the combination of RGB cameras and data processing methods make it possible to non-invasively extract the movement from the entire body. And this can be useful for rehabilitation purposes in the home setting. On the other hand, dedicated wearable sensors or just those embedded in consumer smartphones or smartwatches can be used to analyze specific human movement. And these can provide very useful information on alterations and disorders that they can reflect the risk of fall and the effect of drugs or interventions. So with this, I would like to thank you for the attention. And if you have any question, I will be glad to answer you.
Thank you, Luigi, for your presentation. Thank you very much. I don't know if we have some questions. We have some minutes we can use, but anyway, we can also leave the question for at the end of the workshop. Just a curiosity, or if you have an idea, or in general, if you consider, or if you see in some of your research and application the possibility to have something stretchable could be useful. You already talked about textile, but anyway, to have some stretchable electronic, as in the case of SINTEC or something like this, could be useful in Parkinson, I don't know.
Thank you for the question. I think that it could be very useful. Indeed, we are working on two, parallel directions. From a certain point of view, we are dealing with consumer devices like smartphones and smartwatches, because people already own this device, so they don't need to buy additional hardware. but the measurement accuracy and the list of possible parameters that you can record with these consumer devices is not comparable to those that you can record with smart patches. So in this case, of course, smart patches would be more precise, would include much more, physical and physiological variables. They are more precise because they are attached to the skin, so you avoid movements, artifacts. They are more accurate, and so on. So I would say that these two roads can be parallel, and then can be used from one end for a gross evaluation using consumer devices, and for the other, very specific information can be derived using smart patches. So yeah, of course.
Thank you, Luigi. So
Thank you.
I think that if there are no other questions, we leave obviously the discussion at the end of the meeting. Thank you again, Luigi. We can go with Fernanda. So Fernanda we talk about something more specific, application more specific related to the sleep disorders and this kind of things. So I leave it to you the floor, Fernanda. Thank you.
Yes, good morning, everybody. I'll try to share my presentation. Can you see it?
At the moment, we can see you, not the presentation.
Okay, now?
Not on my PC. I don't know if
We tried a few minutes ago together.
yeah, you but as usual, so
Of
it's
course.
normal. Of course. So you changing a lot the different platform to do the meeting.
What about now?
No, not already. Maybe Fernanda, try to switch off the camera. Maybe it's more simple to understand, or something is going to in conflict. Okay, try to share now.
What about?
There is unfortunately no difference. Sarah, could you have a check if there is anyone else? I mean, it's not anything shown sharing, but is it marked as sharing? Here's something.
Okay.
Here it comes. Perfect.
Okay, Fernanda, we have.
Okay, so thank you, everybody. Thank you, Alessandro. My name is Fernanda Herrera. I am a professor at the Sapienza University in the Department of Electronics. Together with my PhD student Manoni and Dr. Gumiero Alessandro and Dr. Della Torre from ST Microelectronics in the Agrate site, we developed a wearable device for domestic screening of sleep apneas. The work could be carried out thanks to the precious collaboration with Dr. Pellegrino and Dr. Palange of the Hospital Umberto I, which is the hospital of the Sapienza University. Sorry, I don't know why I cannot go on. Okay. So this is the outline of my talk. First of all, I will introduce the concept of sleep apneas. Sleep apneas are sleep-related breathing disorders, which are defined essentially as airflow cessation in the case of apnea, or a strong reduction, I mean greater than 90% in the case of hypopnea, for a time longer than 10 seconds. Approximately 1 billion patients are affected by sleep apneas worldwide, a portion of which are children. there is an index which actually grades the severity of the disease and decides the entity and the type of therapeutic intervention. As we can see in the plot below, the percentage of survival after a certain number of years from the diagnosis dramatically decreases as a function of this index. So it is important to understand the severity of the disease in order to intervene with the proper therapeutic solutions. So why it is so severe, this disease? Because you have to think that patients do not sleep well every night of their life. So they feel daytime sleepiness, which also induce attention loss, memory loss, but also depression. And all these increases the probability of accidents, both in the car while driving, but also at work. But also we have the onset of hypertension, heart disease, insulin resistance, and all these are serious harm to health. We have at least two types of sleep apneas, which often manifest in a mixed way. So we can say that we have three types of apneas, which are obstructive, central, and mixed ones. In the case of central apneas, the brain does not give the command for performing the respiratory act, and it cannot be cured naturally. In the case of obstructive apneas, we have a mechanical obstruction of the airways, which can be due to anatomical problem, and in this case, it can be completely eliminated by surgery, but can also be due to obesity, and in this case, it can be progressively mitigated by slimming. Anyway, in the case of obstructive sleep apnea, we have repeated chest efforts in order to perform the respiration, but it is not useful. So you can understand that the distinction between central and obstructive apneas is fundamental in order to find the correct solution to the problem, if there is the possibility. In any case, all the types of apneas can be treated through forced ventilation by an equipment which should be worn through night, and it is not very comfortable, as you can see in the picture by the side. The gold standard for sleep analysis is polysomnography. Polysomnography gives exhaustive report and it is extremely reliable, but it has so many drawbacks. First of all, it is a very specialized equipment and it needs specialized staff. Very often it needs to be performed in hospital. So it is scarcely available, and there are also very long queues. Then it needs a lot of wires, 20, 30 electrodes disseminated all around the body and on the scalp, and also gel, glues, and so on. We can say that it is cumbersome and obtrusive, and it alters the sleep itself. So often patients need to repeat the polysomnography more than one time. And for all this reason, it is not well tolerated. So the consequence is that most patients remain undiagnosed. For this reason, a wearable device for performing this kind of analysis in domestic environment is highly desired.
And we propose Morphea. Morphea is a wearable device, very friendly, compact, and also cheap, since it uses the technology of integrated electronics. It can be used in domestic environment and monitors the respiration activity. It detects apneas and, very important, distinguishes between the obstructive and the central apneas. Of course, it is not an alternative to polysomnography, which is much more complicated and exhaustive, but it may allow a pervasive, I should say, a massive pre-screening. So deciding if the person actually needs to perform the polysomnography. Shortcutting cues and allowing a more efficient use of the national health system. This is the board of Morphea, which on one side mounts a photoplethysmography sensor with 2 lights and low noise electronics and ambient light rejection. On the other side, we have an inertial measurement unit with accelerometer and gyroscope, and also the system on chip embedding Bluetooth low energy and a microcontroller. All communicate by E2C. This board is packaged and connected to a battery by a very short wire. Then it is positioned on the nasal septum, as you can see in the picture. So let's move to a short description of the 2 sensors. The photoplethysmography is an optical technique. It is very well known since it is used to measure SpO2. It can operate in reflection or transmission, and we use it in reflection mode since we put on the nasal septum. We have 2 lights, red and infrared, which enlight tissues, and the photodetector collects signal from the reflected light. The photoplethysmography signal is related to variations of the blood volume. In particular, we show the photoplethysmography signal on the top, which is due to a DC component due to reflection from bone, tissue, and skin, and to oscillating components, which are respectively due to arterial blood volume variation at high frequency and at lower frequency variations of the venous blood volume. If we look at the fast Fourier transform of this signal, we have indeed a peak related to the venous blood volume variation, which is related to breathing component, and at higher frequency, the cardiac component. The cardiac component is the one usually used in commercial devices to measure SpO2, but we focus on the contrary on the breathing component at very low frequency. So positioned on the nasal septum, the PPG sensor can detect modulation related by breathing at its best. And indeed, if we look at the picture below, we have the amplitude of PPG as a function of time during a normal respiration. The blue curve is the the PPG signal. The red curve gives you the upper envelope. As you can see, it is rather periodic and regular when the respiration is normal, but if we have an apnea, we can see that the signal is completely quenched with respect to the normal breathing. And the in time domain and in frequency domain, we can process the signal in order to build up our algorithm for the detection of apneas. So If on one side the PPG can detect apnea, on the other side it cannot classify the type. And we saw that it is very important to classify the type. We recall that in the case of obstructive type apnea, the person has repeated chest efforts, while in the case of central apnea, the chest efforts are not present. So we focus exactly on this feature, on the chest movement, in order to distinguish between obstructive and central apneas. Indeed, the chest movement propagates to the head and can be detected by the accelerometer positioned on the nasal septum. If we look at this picture, we have here a mixed type apnea. The accelerometer amplitude is drawn as a function of type. It starts with a central apnea, and then approximately at second 65, we have the onset of the obstructive apnea. As you can see, the two signals are completely different, and we can rely on this, in particular in frequency domain, to classify the type. So let's very rapidly see the two algorithms. The block scheme for apnea detection are shown here. We have as inputs red and infrared PPG signals. Then we have two distinct detection methods in order to be as more robust as possible. Method 1 is in frequency domain and processes the power spectral density of red and infrared signals. Method 2 is based in time domain and processes the pulse width amplitude only on the red signal. The two methods calculate the average values on the overall traces, method 1 of PSD, method 2 of the pulse wave amplitude, and we call this threshold. Then we move to instantaneous values, which are defined as the average values in very short windows. These windows are moving, of course, second by second. The comparison between the threshold and the instantaneous values can give us flex. So, in the case that the instantaneous values are greater than the average on the total trace, we have a 1 flag, which corresponds to the onset of the apnea. Then the output of these two methods are enter gates, and one receives flags from red and infrared from the PSD method, and two receives inputs from red light from the PSD method and from red light from the pulse width method. So as you can see, we give more importance on method 1 and also on the red light. The output of these two AND gates enter an OR gate. So if AND1 or AND2 are 1, we have as a final decision the apnea. In this slide, maybe the concept is well explained. We have on the top method 1 on red, then we have method 1 on infrared, then in the third row we have method 2 on red, and then at the bottom we have the final decision. As one can see, only when at least method 1 has a 1 flag, or method 2 has a 1 flag, we have a final decision of apnea. In this case, for example, with the dashed line, we had actually a 1 highlighted by method 1, but it was only on the infrared. So as a result, we had a 0. As for the apnea type classification, we invoke fusion between the two sensors. So we have the PPG, which had defined intervals where the apnea occurs, which are highlighted in this plot with the red rectangles. Then we consider the wall accelerometer trace, which is drawn with the blue curve here. Okay, so let's select the accelerometer trace only where the apnea was highlighted by the PPG. And in those very short interval, we calculate the power spectral density of that specific episode of apnea in the respiratory band. Then we consider the wall trace and calculate the average power spectral density, which we call threshold. At last, we compare and take a decision. If the comparison is that the instantaneous values in that specific episode is greater than the threshold, we have an obstructive. And indeed, we can see that in the first, second, and third window highlighted by the PPG, we had obstructive, and in the fourth, we had a central apnea type. Let's now move to test. We tested the patient. She was a female, 52 years old, and was very obese. She had previously a diagnosis of very severe apneas. Actually, she had the AHI index greater than 100 from previous polysomnographies. The patient was hospitalized and was subjected to polysomnography while wearing our device on the nose. The acquisition lasted the whole night. As a result, the polysomnography detected 545 apnea episodes, which is actually a very huge number. And Morphea detected 483 with a sensitivity, a calculated sensitivity of 88%. Morphea also detected false positive, 37 false positive, with a calculated precision of 93%. So we can say that the detection performances of Morphea are excellent. But what is more important for clinicians is that Morphea made an excellent grading of the severity. Indeed, polysomnography calculated 102, Morphea calculated 104, and this is the index which allow clinicians to decide the proper therapeutic intervention. But also it is very important that Morphea classified correctly 100% episodes of apneas detected. They actually were mainly obstructive, and Morphea detected correctly all the obstructive and also all the centrals. So let's move to the conclusion. Morphea is a wearable device for monitoring sleep apneas in domestic environment. It is positioned on the nose where the photoplethysmography sensor can detect apneas at its best. Also positioned on the nose, the accelerometer can detect movement propagating from chest efforts to the head. The contemporary use of photoplethysmography and accelerometer allows classification of apnea types. In the test, Morphea yielded excellent sensitivity in detection exact grading of the severity and exact classification of the apnea type. I wish to underline that we made just one test, even if the test was very meaningful since the number of apneas was huge. But it is not so easy, as you can understand, to find patients which accept to perform this test. Others so wish to thank the patient, and also I wish to thank you for your attention.
Thank you so much, Fernanda, for this presentation. I think it was very interesting. And I don't know if there are questions about. Obviously, I can just ask one thing, but really just to maybe for the audience, is the same for Luigi. But in this case, I think that there is very good reason that we say, real reason to say. You can see the stretchability of a solution be useful in this case. I think maybe it's obvious, but maybe you can give us some idea or something more.
Actually, Alessandro, I thank you for this question. Also, because I thank you very much for this question. Also, because as you know, I am involved also in our projects with you mainly, which involve observation and long time monitoring of biosignals and vital signs, as in the case of the sleep-related disorders during the REM phase or hypoglycemia vital signs, and also in Parkinson's disease. A lot of I use a lot of sensors disseminated on the body for monitoring a variety of different diseases. And the use of stretchable in this case specifically, but also in all the other cases, would be really, really important in order to make, because all these applications are based on the fact that they are comfortable and can really introduce a disruption with the conventional method, because people wishes to monitor their disease, to also wish to have much more empowerment of their disease. And this can be obtained only if patients are accept to wear all these devices and to be subjected to long time monitoring in domestic environment. Also, only in this case, telemedicine in general and long time monitoring in health can have a real success.
Thank you, Fernanda. I think that class, you have some question?
Yes, thank you. And Fernanda, I'm truly inspired and interested in this research. But I followed, there is some Israeli groups and they have this company Xtrode. Do you have any experience with their wearable systems, and if there are any pros and cons if you miss information or miss sensoric data that they can provide compared to what, for example, ST Microelectronics could provide?
No, thank you, Klaas. I don't know the work by this group, and maybe you can send me.
I will definitely send it to you. No problem.
Yeah. Thank you.
Enjoy. They are quite interested, but I personally believe that one should combine electrophysiological sensoric data with biomechanical sensoric data to get a more full picture of sleep behavior and sleep analysis. And I think that is what they are missing. So just to give you a hint, what I want you to look upon.
Okay, thank you. I
Thank
wish
you.
just to spend a few words more about sleep, because we are currently working with Alessandro and Luigi from SITEC on another wearable device exactly for monitoring the REM phase. Because as already Luigi said, there are prodromes of Parkinson's disease, but also of other neurological diseases in the phase, specifically in the REM phase of sleep. So we have developed a wearable device which detects biopotentials with the QVAR. And this involves a single channel of electroencephalogram and the electrooculogram as an artifact of this single channel electroencephalogram. Then we monitor the electromyography of face muscles, and finally the heart rate variability using just two QVARs and one PPG sensor on the head here on front lobes. And I think that if we prove that it works, we just proved one time, but we have to achieve more results. It will be rather disruptive, I mean, because you can use it in domestic environment, and it is a predictive tool, you know.
Yeah, I totally agree. Of course, you always want more. So of course, I would like to see breathing patterns and movement patterns as well. But what you bring up is the essential. I totally agree. Thank you so much.
You're welcome.
Thank you for this discussion also. And but in general, just to conclude this argument, I have to say that joining the two things to be able to detect signal coming from the face for the apnea or for the diseases, neurological diseases, and couple this with a more comfortable way to do so, stretchable manner, and also with class already discussed with on the let me say the shape or the possibility we have with SINTEC technology could be a real good things for this kind of environment and application. So it's very interesting, I have to say, field. Thank you, Fernanda, for the presentation and also for the discussion. So I will leave the floor to our last speaker, so Laura, that as we usually said, not the least, but just only the last, and that we will introduce, we talk about something more related, let me say, to the market and to the practical way to use this kind of object, and maybe where this kind of discussion and things related to the comfort and the usage are very interesting, because at the end of the story we would like to guarantee to simplify the usage of these devices. But anyway, we are listening to you, Laura, please. We have some problem with the phone, with the microphone.
Can you hear me?
Good.
No?
Yes, very well.
Okay, it was just mute. Okay, sorry. So thanks, Alessandro, and good morning, everybody. As Alessandro said, I'm product manager working for CSM Telemedicine, which is a business unit of Compro Group medical company dedicated for the development of solution in the telemonitoring and telemedicine field. And we will try with this presentation to give you an idea about how we use the solution you are speaking about into the market, and we will try to give you some idea about services and use case we have ongoing right now, and some inputs about on how we can improve the actual solution. So just a few words about the company. Okay. Compro Group Medical is a multinational company with the headquarters based in Germany. And the only focus of the company is to develop software solution used in the healthcare fields. And we are based in Italy, and the main market is the outpatient. I don't know why it's very slow, the slide. Okay. So in the Italian market, we are mainly present in the providing software solution in the pharmacies for the GPs and the single physician specialists, and for the dentists. And only our business unit as CSM Telemedicine is working within the hospitals, providing solution for the telemonitoring and the telemedicine field. So as CSM Telemedicine is the new name of the company. The company at the beginning was named HNS, which means hardware and software, and was an Italian company that was acquired by the group in 2020. And at the moment, we have over than 20 years of experience in design and development of software and hardware solution in the specific vertical field, so in the telemedicine field. And as we see in these slides, we have all the certification that are needs in order to design and develop a medical devices solution. And of course, we follow all the GDPR regulation in order to provide these kind of services. Okay, our main solution in the telemedicine fields is a software solution which and have the aim to follow the patient in the entire patient journey. So we develop solution for the prevention, for the diagnosis, for the monitoring, and taking charge of the patient. And the solution aim to be modular, so that based on the specific service that the client need to provide, can activate or not some specific modules. And it's also scalable because it should be used in from the single physician to group of hospitals. And it's also integrated because we have integrated within the solution of our company, and we integrated with external solution, for example, hospital information system, the electronic health record of the regions, and so on. And here you see just a plot of our solution, for which the core of the solution is the CGM Care Map, which is the web-based platform, and used to manage basically the telemonitoring vertical, and in particular we have some vertical in cardiology we will look for after. that. We have a solution to manage the point of care, which is mainly the telerefertation. So second level examination that should be performed in different places and should be reported from physician remotely placed. We have modules for the taking charge of the patient in order to improve the drug adherence and the blistering, so supporting the patient in taking the right medication therapy. And we have a module for the video consultation. And as you can see, this should be used both in the physician, for the GPs, in the pharmacies, in the hospitals, and for the domiciliary care. That's just an overview about the different modules we have integrated within our core platform. And as I said before, in the telemonitoring field, we have a solution for primary and secondary prevention, the telemonitoring of chronic patients, and for basically the most common chronic disease, which are the COPD, the heart failure, the diabetes, and the hypertension. And we have a vertical on the cardiological telemonitoring. The core of the solution in the cardiological field is a device that already Alessandro showed you, which is the ECG HI device, which was designed by ST, and we support ST with the certification of the device as medical device, and we have right now the exclusivity of the commercialization of the product in Europe. So I will not go into the details of the technical specification of the device, because I already know that you know that device, and probably you use it also in the first step of the SINTEC project. I just would like to underline that our development team, our development job was mainly focused to integrate this device within our telemedicine platform and solution to provide on the market different services within the telecardiology field. So basically, we integrated the device within our platform, so the data are transmitted via Bluetooth from the device to a mobile application that we developed, which is the first interface of the patient in order to use properly the technology and give to the patient different inputs about the status of the device, which should be the battery level, the electro status, and the Bluetooth connection. And additionally, we develop some specific function, for example, to be able to track the status of the patient, and we develop a digital diary for the patient, and the patient is able to view the ECG lead within the application.